Filippo is going to continue his short course with no hair theorem and black holes.
Thank you. So, thanks again for coming, first of all. Just a very quick recap of two things that we have seen yesterday, which might be useful. So we have reviewed the no-hair theorem. Basically, this states that whenever we have a stationary black hole solution, which is a solution of Einstein-Maxwell's equations of general relativity, then the black hole will, during the gravitational collapse, will radiate away all those characteristics which are not directly related to mass, spin, and electric charge. And I would like this to be stuck in your mind for the moment. Then we have also seen the Maxwell's equation in curved background, and there is one formulation. There is one formulation which is particularly illustrative, I would say, which is the 3+1 decomposition, in which basically we adopt the perspective of a certain finite observer called the normal observer, or the zero angular momentum observer. And in this formalism, the Maxwell's equation takes the same exact form that it takes for standard electrodynamics in a medium. So in this sense, we can think a bit about the space-time as it is a medium, characterized by a certain vacuum permittivity, which is given by the Laplace function, and where the frame dragging effect, so the shift vector, is related to the generation of a polarization or of a magnetization. And also, this will play some role in our discussion today, because what we're going to do now is to see some solutions of Maxwell's equation in curved background, in black hole backgrounds actually, and we will start with the simplest case. Of course, the simplest scenario is the vacuum electromagnetic fields. And an even simplest case is that we have a non-rotating black hole. So we start, for the moment, we will start with the Schwarzschild solution. The black hole is characterized by a certain mass, but it's not spinning. This is just the Maxwell's equations that we have seen before. As I said, we will focus basically on vacuum solutions, or I would like, maybe it's better to say quasi-vacuum solution in a sense. I will explain this in a second. We will also restrict to solutions which obey stationarity and axis symmetry, which are the symmetries, the isometries of the background. This, I would say, is a kind of a natural simplification. So, first of all, we have said isolated black holes cannot have electromagnetic fields, or better, they can have it if they are charged. So if the Einstein's equations are coupled with the Maxwell's equation, but this is not the case in astrophysics. The only possibility then is that black hole is uncharged. This is the most likely scenario, and this is the case that we consider. Moreover, we will consider, in this case, non-isolated black holes. In which sense? We have the metric, which is fixed by the Schwarzschild space-time. On top of this space-time, we will put a test field, a test electromagnetic field. Test means that the energy momentum tensor associated to this field has an energy scale which is still much smaller than the natural mass scale of this Schwarzschild black hole. And we will see two basic examples. The case of a magnetostatic field and the electrostatic field. So these were examples which are classic in the literature of black hole electrodynamics, and which were, as you can see, they were worked out during the 70s. Black hole electrodynamics is quite an old subject, but it's still a matter of current research. So our objective today is to understand what is the effect of having a black hole in these configurations. And we will start with the magnetostatic field, because are the most relevant for astrophysics, let's say. They are still quite artificial, but I mean, as you can see, the configuration that we choose is, as you can see from this beautiful picture, the configuration that we choose is that in which we have some sort of stationary and azimuthal current. So we have a current loop running along the equator of this large black hole, and since we have a current, it is natural that this current generates a magnetic field. So the black hole has, in some place nearby, at radius r equal b, a source for the magnetic field. So we want to understand how the magnetic field in the space-time will look like. To solve this problem, of course, we need to turn on some magnetic potential. In this case, since we are in stationarity and axisymmetry, the only relevant component of the magnetic potential is the component phi of the gauge field. And the current density takes basically this form. So we have a certain value for the intensity of the current. There is a factor which is to make this object covariant, let's say. And then we have two Dirac deltas which localize the current precisely at the equator. So where the cosine is equal to 0. Check. Check, okay. And precisely at r equal b. Now, if you restrict to this configuration here, the Maxwell's equations that we have seen before will take this expression. So basically we have a certain differential operator acting on the azimuthal magnetic potential. This is equated to a certain source for the equation, which is given by the current, of course. This differential operator makes the Maxwell's equation take the form of a partial differential equation. So you can see that we have derivatives in the r component and in the theta component. Now, solving partial differential equations is, as you know, quite complicated in general, but this system is sufficiently easy to address. And in particular, we can exploit the fact that this part-chilled spacetime has some separability properties. In particular, we can make the ansatz that the azimuthal potential will take a separable form. So we have a certain radial eigenfunction function and a certain polar eigenfunction function. In this way, we can basically separate this differential operator, and the separation will be such that we have to solve a system of two coupled Sturm-Liouville problems, which are basically eigenvalues problems, let's say. So let's see more explicitly. So in particular, when you plug this expression into this differential equation, you will be able to separate two contributions that must be solved independently, one from another. So the one contribution is that for the angular harmonics, angular eigenfunctions of the system. And this expression has basically the form of a Papperitz-Riemann equation, where where I didn't mention this, I didn't write it explicitly, but this L is a separation constant. Basically, it serves us to count what are the harmonics of this system. And it will only take 0 to positive values, integer values. So, being this differential operator, which is listed in the literature, well, sorry, I skipped an important passage. Here, in order to solve this differential equation, actually, what we need to do first is to understand how the homogeneous equation works. Once we know the homogeneous solution, we can use and combine the homogeneous solution together with the source term for instance, by means of the green functions method, and construct the full solution of the system. First of all, it is important to understand how the harmonics, how the eigenfunctions of this differential operator works. So coming back to the angular harmonics, this is an equation that we know how to solve explicitly. If you plug it into Mathematica, it will give you the right answer, basically. And the right answer is that we have a set of two hypergeometric functions. This can be rephrased actually in this context as two Gegenbauer polynomials. And, well, that's it, basically. This is the angular part. We have a set of angular harmonics which is captured by these exact expressions. And we will see them later more explicitly. But now we have to solve the radial part. Also, the radial part, as you can see, is very similar. And actually, also this differential equation is of the Paperitz-Riemann type, which means that the most general solution is always some kind of hypergeometric functions. Actually, if we can we remove that part from the screen? Is there a way? Because there's some. Well, okay, whatever. I will tell you with words. So we can solve this equation. The solution in general is given by hypergeometric functions, which are different from the usual one. In this case, they become Jacobi polynomials. As you can see, we still have the separation constant, which counts the radial harmonics. Yes. Okay, that's fine. Oh, thank you very much. Yes. So, when we try to solve this equation, we actually typically derive this solution. But we have to be smart, because in this case, in this type of equations, once we have a solution, we can always consider also a dual solution, which is obtained by means of this integration. And this integration will generate a new kind of solution. And both of these will turn out to be very important for us. So, because the first one, the U solution, if we analyze the asymptotic behaviors, we will see that it will always diverge at the asymptotic, at the radial infinity. It will diverge like r to the L plus 1. On the other hand, this solution is always regular at the event horizon of the black hole. So this is a good solution to use when we are very close to the black hole. If we look at the dual solution, then we have the opposite behavior. So when we go towards the radial infinity, we have some regular behavior, whereas we have some sort of logarithmic behavior, which is close to the horizon. And this, in principle, is not a problem as far as we talk about the magnetic potential. But it's a problem when we take derivatives of the magnetic potential, because the field will be divergent at the horizon. So this is a good solution to be used asymptotically, let's say. And the idea is that this problem, like many problems actually in black hole electrodynamics, can be solved by means of a matching. But first, let me go a bit deeper in the homogeneous case. So let's forget about this source term for the moment. In general, every vacuum magnetic field is partial, can therefore be written as a combination of the harmonics that we just constructed. So we will have all these harmonics summed together. I isolated this term for a very simple reason, because the theta zero contribution is actually associated to a monopole magnetic field. And this is always a solution of electrodynamics, of vacuum electrodynamics in particular, because if we are in vacuum, the solutions of the equations of electrodynamics can be always dualized. There is no breaking of symmetries, right? So we have a monopole magnetic field here. Now, it seems strange, but actually the monopole magnetic field plays a very relevant role in astrophysics, because we can be smart and use a certain trick. So the problem with the monopole magnetic field is that all the magnetic field lines have a unique polarity. Okay? So this doesn't allow you to preserve the Bianchi identity. The field is not solenoidal. But what you can do is to cut the solution and reverse it at the equator. This is something that you actually can do, but you have to pay a price. And the price you pay is that there is a discontinuity in the perpendicular component of the magnetic field here. And since you have a discontinuity, the junction condition always say that there is some kind of source in that place. And the price that you pay, therefore, is that of introducing a layer of current in the equator of the black hole. This, which seems a rather artificial solution, is actually what is often observed in simulation. And this layer of current has physical properties, is called a current sheet, and probably we will see some effects related to current sheets in tomorrow's lecture. But I just wanted to mention that rather than being a disadvantage, the monopolar configuration is kind of interesting because it's simple, first of all, and because it might make sense for us. So yeah, I didn't say, but this configuration is called the split monopole magnetic field. Now, if we move to the first harmonic, what we have is by using the solution, the radial harmonic, which is regular at the horizon, we find some configuration like this. So this is like a black hole immersed in an external uniform magnetic field. So it is uniform because, as you can see, the field is basically regular for r which goes to infinity, theta which goes to 0, and this combination kept fixed. So it means that you can move only along the vertical direction. So this represents this kind of harmonic. I recall that we are making a decomposition in harmonics here. This harmonic represents a uniform magnetic field. Then, what do we have if we consider the same harmonic, but instead of using U, we use U bar? What we have is a dipole field, which, I mean, it's a great field, right? Because this is what we are used to when we talk about the magnetic field. If you look at the magnetic fields of neutron stars, typically it has a very strong dipole component. And I mean, that's a great field, but the problem is that we have an horizon divergence. So here we learn something, namely that stars, which have surface, and the surface is always located outside the gravitational radius, can effectively sustain a dipolar magnetic field. But this is never true for black holes whose surface doesn't exist, in the sense that it is hidden inside the horizon if it exists. So this is something important to remember, because one might think that this is the most natural field to consider in astrophysics, and probably it is not. I mean, definitely it is not for black holes. So this is just a parenthetical remark about how these magnetic eigenfunctions work. So let's move back to our problem. we still have the current to plug into the equations. But now we can do it because we have a natural set of eigenfunctions to which we decompose the problem. And once you decompose the problem, basically it takes this form where we have some coefficient, some radial function. These are not radial harmonics because they will be influenced by the presence of this current. And we have some theta dependence. In particular, you can notice that I excluded all the terms which are even in the separation constant L, and this because the even harmonics has some unwanted feature in our case, namely at the equator the magnetic potential goes to zero, and this is not what we expect in this context. So we will keep all the only the odd harmonics, and we just have to impose that all the harmonics on one side match all the harmonics on the other side. So, as I told you before, while we are close to the horizon, and here we have a natural scale set by the position of the current, we can very well use the U eigenfunctions. On the other hand, when we are outside the horizon, we can use the U bar eigenfunctions, which are regular at infinity. And this allows us, by means of a matching, to construct a full solution around the space-time, which is given by this. So this I plotted with Mathematica by just plotting this. Of course, you have to impose also that the derivatives of the magnetic potential match each other, because the derivatives are the field, and we want the field to be continuous. But here you can see basically the magnetic field line of this configuration, where the red point represents precisely the current which is orbiting around the black hole. And I mean, you look at this picture and you might say, okay, but this is rather similar to a dipolar field. Well, it is actually not, because here we have actually superimposed an infinite number of harmonics. To generate this plot, I superimposed like 20 harmonics, but like the full solution in principle has an infinite number that you should consider. So this is actually not a dipole, and remember that a dipole is never regular at the event horizon of a partial dipole. Moreover, if we send B, so the position of the current, this red point, to infinity, what we obtain is that basically only the first harmonic remains, and we have a black hole immersed in an external uniform magnetic field, which is what we expect, because a current pushed at infinity will generate a uniform magnetic field. But what happens if we push the current towards the black hole? Well, in this case, we have to be consistent with the no-hair theorem. And the no-hair theorem says that a black hole, if it has some magnetic properties, must be only dependent on the electric charge, which this black hole doesn't have. So in this case, everything must vanish. And indeed, you can see from this matching coefficient that if we push P towards 2m, basically we kill the solution. So we don't have a magnetic field. And this is, in a sense, this is a way in which this system is consistent with the no-hair theorem. Of course, like the no-hair theorem is a dynamical statement, but here we can think that this is a sort of quasi-stationary situation in which at every instant we push the current closer to the black hole until the field completely disappears. So yeah, just a rephrasing of the no-hair theorem. The multiple moments of the field are radiated away when the source approaches the black hole. Okay, this was the configuration discussed by Peterson on 1974. Now,
we can also consider like another configuration, which is the electric counterpart of this. I will not enter into in the mathematical details. In this case, of course, we are talking about an electric field. We have a static charge placed at some point around the black hole. In this case, I put it on the vertical axis, but you know, Schwarzschild as a symmetry, as a spherical symmetry, so it doesn't really matter. We have to turn on an electric potential, so a T component for the gauge field, and the charge density will look this way. So even in this case, we have a differential operator. The differential operator can be separated. The separation leads to angular harmonics, which are, in the electric case, Legendre polynomials, and radial harmonics, which are, oh, which are some hypergeometric functions. Doesn't really matter. But the game to play is exactly the same. Even in this case, we have to match the inner solution and the outer solution at the position of the charge. And what we obtain is some configuration like this. So here we have our charge, and here we have our black hole. In this case, the charge is placed at 4m. Now, when we push the charge towards the black hole, again, we have to be consistent with the no-hair theorem. And in the electric case, the no-hair theorem states that the black hole, a static black hole, can possess a monopole charge. Indeed, when we tend towards the black hole, asymptotically the fields becomes monopolar. So this is a sort of a Reisner-Nordstrom mimicker if we think about it, right? It's also interesting to notice that if we place our charge here, so this is taken by the paper by Hanni and Ruffini. If we place our charge here, then we will have some electric field lines entering the event horizon and also escaping the event horizon. This is possible because these are space-like objects and can always happen. But we can think about the surface of the event horizon as it is at the surface of a conductor. And in this sense, we can think that every one of these charges entering the horizon is attached to a certain electric charge with negative density here and positive density up here, so that you can actually derive a certain distribution for the superficial charge density of the black hole. And this was made more formal in a sense during the 70s with the idea that one can, in a sense, endow the black hole with a sort of membrane which is just placed outside the horizon. This is called the stretched horizon. And this idea, which is called the membrane paradigm, basically states that the black hole horizon, or better, the stretched horizon, can be considered as a kind of a surface enclosing the black hole, which is characterized by certain universal properties. In particular, you can check how the electric, magnetic fields and the currents work in this regime very close to the black hole, and you will observe some interesting facts. For instance, the electric field at the horizon is always related to the electric current at the horizon by a certain value of the effective resistance of this membrane, which is 4 pi, which, if you convert it into international system, is 477 ohm. So every black hole apparently is characterized by this effective resistance. So this I presented here because I think it's a rather interesting idea. The idea of the membrane paradigm is also still used in some context, like in the fluid gravity correspondence or in ADS-CFT, but is rather outdated in the context of astrophysics. Like at the beginning, this membrane paradigm was considered to be a possible explanation for the Blunt-Forest-Nyack mechanism, in the sense that if the black hole is characterized by a certain surface, then the magnetic field lines that attach at this surface generate a torque over the surface of the rotating black hole, and this torque is what extracts the energy from the black hole. But actually, this picture makes things extremely more complicated in terms of causality. So now the point is that we don't speak about energy extraction mechanism anymore in terms of the membrane paradigm, but in terms of the generalized Perron's processes that I told you about yesterday. So everything that we have seen so far is about Schwarzschild black holes immersed in external electromagnetic fields. Now we can think what happens if we relax the hypothesis of a Schwarzschild black hole and we consider a stationary black hole. So it can be a Kerr black hole, but actually this derivation is more general. So we still consider non-isolated black holes, in the sense that the black hole now is spinning, and we are interested in understanding what are the effect of the black hole spin, which is still a strong gravity property of the problem. When the black hole is immersed in an external magnetic field. And the starting point is remembering that stationary and axisymmetric black hole spacetimes must be solution of Einstein's field equations in vacuum. And also that stationary and I said space-time, but I meant black hole spacetimes. And also that stationary and axisymmetric black holes are characterized by Killing vectors, one for stationarity and one for axisymmetry. And the Killing vectors obeys the Killing equation. Now, one can interestingly, and there was one, which was Robert Wald, asking himself, what happened if I consider that the the gauge potential is actually related to one of these Killing vector fields? What can I get out of that? And so we plug the Killing vector inside the field strength equation. We can use some properties related to the Lie derivatives and to the Killing equation to kill this term and rewrite the equation this way. Then of course, you want to consider the Maxwell's equations in order to have solutions. So you take the derivatives of this object. And once you take the derivative of this object, you have to play a lot with the combination of the covariant derivatives. As you might remember, like when you take the commutator the commutator of two covariant derivatives, you generate the Riemann tensor. And this is precisely what we obtain here. So this is the Riemann tensor of the space-time, which is 0 by definition for black holes. So what we obtain is a solution of vacuum Maxwell's equations in a black hole space-time. So basically what we have learned is that the black hole isometries, the Killing vectors, can be used as natural gauge potentials to generate vacuum field solutions of the Maxwell's equations. So now we have to, of course, it is not said that just because you have a solution, this is physically relevant. Of course, you want to respect some natural properties. We want the solution to be stationary and axisymmetric, but this is kind of guaranteed. We want the field to be everywhere non-singular outside the event horizon. This is not so obvious, like we have seen before with the dipolar field. And we want the electric and the magnetic monopole charges to vanish. Now, let's see what happens if we consider, in the case of the Kerr metric, the two Killing vectors associated to this black hole. In this case, we can estimate the monopole charges by just taking the integral of the two form associated to the field And since we are talking about killing vectors, these integrals actually becomes Komar charges, Komar integrals, which basically it tells you what are the physical monopole charges as seen by an asymptotic observer. And we can see that in both cases we don't have any magnetic charge, but we do have an electric monopolar charge. This is something that we don't want to have, of course. But since a linear combination of of two killing vectors is still a killing vector, we can mix these two fields and construct a natural solution which has vanishing electric and monopole charges. And this solution is what we called the Wald solution, which is really a milestone of black hole electrodynamics. Because if you also if you look at the gauge potential, this is a rather simple expression. Of course, in order to derive the fields, you have to take covariant derivatives, and those expressions are not so pleasant, but we can still understand what is going on by looking at the potentials. And in particular, you have to remember that a killing vector has 1, 0, 0, 0 component only if the index is up. Now we have the index down, so in this case we also have a time and a phi component where both killing vectors contribute. So we have an electric potential and a magnetic potential. It's exactly like the ones that we have discussed before in the case of a Schwarzschild spacetime, but here we are in Kerr, so we can understand what is the effect of having a black hole spin. And we can start with the electric potential, which is written here. And there is something that is kind of important to notice already at this level, namely that we have even in absence of any electric charge, so here we don't have any source close to the black hole, the field acquires an electric component. So we are generating an electric field in a certain sense out of nowhere. And where does it come from? Of course, it comes from the fact that the black hole is spinning. Indeed, if we set the black hole spin A equal to 0, no electric potential anymore. So why a black hole spinning would generate an electric field? Well, the reason is in the Maxwell's equations that I showed you before. Like the frame dragging effect is actually responsible for polarizing the space-time and for polarizing magnetic fields in such a way that they become electric fields. So in a sense, we can think about this electric potential to be generated by the twisting of the magnetic field lines, which is induced by the frame dragging effect. And of course, since we have an electric potential, we also have a potential drop. And this has important implications, because if you have a potential drop, it means that whatever stray particles arrive close to the black hole, it is accelerated by this electric potential and will become relativistic. This is very important for the space-filling magnetospheres. So now we can look at the magnetic potential. What's going on here is that if we look at the solution at infinity, the field looks exactly like the uniform vertical field that I showed you before. So this solution, the Wald solution, basically represents a black hole immersed in an external magnetic field whose source is pushed away at infinity. And if the black hole is spinning, this magnetic field will start a twisting of the magnetic field lines and will generate an electric potential too. So it is rather interesting now to understand what happens to the magnetic flux when it's evaluated at the horizon. So the magnetic flux is always related to the azimuthal component of the gauge field by means of a factor 2 pi by evaluating the gauge field at the horizon and at the equator. And here is the expression that we obtain. which is rather funny because now we see that if we don't have a spinning black hole, of course, the magnetic field precisely match the field of a current loop pushed at infinity, which is what we expect. But it's even more funny is if instead of considering a non-spinning black hole, we consider the extreme case. In the extreme case, when the black hole is extremely spinning, has reached, has saturated the extremal bound, then the magnetic flux at the event horizon is zero. This means that the faster the black hole spin, and the more it will push away the magnetic field line outside the event horizon. And this has a very precise name, which is called the black hole Meissner effect. So, and it's called like this because the Meissner effect is an effect that we have in superconductors. So a superconductor will, if immersed in an external magnetic field, behaves like an electric conductor in a sense, like it pushes away the magnetic field lines from its interior. And the analogy is even more fitting if we think about the Hawking temperature of an extreme Kerr black hole, because when we push the spin of the black hole towards its extremal bound, the Hawking temperature tends to zero. And you have to remember that superconductors work at low temperature. So it seems like, in a sense, that spinning black holes behave like superconductors. So here is it's some representation from for what I have just said, which is taken by a recent paper by Komisarov. So when we have a non-spinning black hole, this is the Wald solution in the Schwarzschild spacetime, which basically just represents a static black hole immersed in an external magnetic field whose source is located somewhere away, pushed at infinity. We don't care where it is. The important thing is that this is a uniform field. As soon as we turn on the rotation of the black hole, what happens is that the magnetic field lines are expelled from the event horizon. The event horizon shrinks also. This is a natural process by increasing the spin of the black hole. And when we reach extremality, you can see that the magnetic field lines become tangent to the event horizon surface and never cross the horizon. So this is precisely the illustration of the Meissner effect. And also, I forgot to mention that these blue regions basically represent the regions of constant electric potentials. So these are the yeah. So this just indicates that whenever the black hole is spinning, as opposite to this case, we also generate an electric field. So you might say, because I mentioned this yesterday, that saying that we have magnetic or electric field is a rather empty statement, because these are non-covariant quantities. That's true, but what is true is that we have frame invariance, and the frame invariant for the Wald solution is always different from zero, which means that no matter what kind of observer you will consider, an electric field with a component proportional to the magnetic field will be always present. And this is illustrated by this plot, where, if I remember correctly, the pink regions goes from -4 to the blue region, which goes to +4. So the fact that the Wald solution is characterized by an unscreened electric field is always present, is an invariant statement. The electric field is always generated by a black hole. It's something that you cannot simply cancel out by means of a coordinate transformation. And this is the main, I would like not to say problem, because it's not a problem, it's just a feature of the Wald solution. Because if we generate an unscreened electric field, then this solution is unstable, precisely for the same reason that I was telling you before about the potential drop. whenever we have a particle passing by, an electric particle passing by, this particle will be accelerated to relativistic speeds by the potential drop. And if a particle is accelerated, it emits photons. The photons are sufficiently energetic to create to charge a pair creation of a couple of electrons and positrons, and basically what we obtain is at the end a space filled magnetosphere, which is what we actually want to study. So there was also some idea that since an extreme Kerr black hole immersed in an external field is subject to the black hole Meissner effect, then we cannot have extraction of energy because the magnetic field lines never touch the horizon. This was actually found not to be true if we relax the assumptions that we are in vacuum. This was first proved by Komisarov, which started with the Wald field, injected some sort of massless matter, and what I've seen is that the field change is shaped and stops the black hole Meissner effect, so it reinserts inside the magnetic field line. And there was recently a very great paper by Kyle Parfrey, Alexander Filippo, Benoit Cerruti, that with a GR peak, so a general relativistic particle in cell code called Zeltron, uh, also obtained the same result by generating a plasma field magnetic field. And now I just went to the Kyle Parfrey website, and I would like to show you the movie because, in my opinion, is rather beautiful. So, as you can see here, we have the black hole, the Wald solution. So the black hole subject to the black hole Meissner effect. Then, from this time, they will start injecting particles with this code. And what happened is that as soon as the particles fill the region close to the black hole, the magnetic field lines start to penetrate inside the event horizon. The black hole Meissner effect is stopped, and we have a charged particle production with electrons and positrons filling the entire region outside the black hole. Then we have some interesting effect occurring here, which we will discuss in a second. But this red line here is basically the same feature that I showed you before. It's a current sheet. It's a layer of current on the equator of the black hole, which naturally forms without basically any assumption. So this is a rather common feature of black hole magnetospheres. Yeah. So in principle, I would have finished for today's lecture, but if there is time, I can also continue. 5 minutes. Okay, but then we continue tomorrow, like because it's a new topic, so it wouldn't make real sense.
Time for questions.
So thank you for the presentation. I would like to ask you a question about the magnetic field of the case of the black hole, which is not spinning. So it's just a curiosity because I want to understand more about the plot. You can actually no, you can pass. It's more about the section about the Wald black Schwarzschild solution. Yeah. So this in this representation, when you have A equals to 0, the magnetic field seems to come in the horizon and come out. But it's because the magnetic field is in the background and the black hole is right there. But I was expecting to see the field lines to curve due the curvature of of the space-time. Rather that I see the field lines getting narrow and narrow.
Yeah.
Yeah. So can you explain a little bit more about that?
Yeah, well, I can. Yeah, I got your question. It's a good question, actually. I never thought about it, so I don't have a precise answer for that, I have to admit. But I mean, that's the solution that it is. Like you solve the Maxwell's equation, and it is what it is. Yeah, I I understand your question, but maybe is also because we are used to think about the motion of particles around a black hole, and uh, particles can have radial directions and or can curve if they have a certain angular momentum. But the magnetic field lines are a different object. They are really one-dimensional objects. So if you think in terms of gravitational potentials, for them it's a completely different world.
I see. I see.
But I really, it's a good question. I have to admit, I don't know how to answer to this.
Okay, thank you very much.
Thank you very much. Since the presence of the magnetic or electric field is observed dependent, right?
Sorry?
The presence of magnetic field or electric field are observed dependent, right?
Yeah, yeah.
So if we take an observer moving around the black hole, rotating around the black hole,
Mhm.
can we see something similar to the Kerr case or something?
If it is
For example?
immersed in the world in the so you say I got a static black hole immersed in an external magnetic field. Then I take the perspective of an observer orbiting around the black hole, and I should see eventually electric fields being generated. It's true. You can have it. It's not the same situation as in the world case for an extreme black hole, precisely because of this. So this is an invariant statement. And this statement, it says there is some component of the electric field which is along the magnetic field lines. And this is true for this case. If you take the observer orbiting around the black hole, this will never be true because once you have this equal to zero, it must be zero for every observer. So eventually you will have an electric field, but it will always be perpendicular to the magnetic field lines.
Okay, thank you. Any other questions? So let's thank Filippo again.